You know about this. And as I've reminded you, if you've got a legitimate conflict with Thursday's exam, for example, maybe you got 46L, give me a note. On the note, indicate the nature of the conflict and at what earlier time slot Thursday you can take the exam. Noon to 2 p.m., 2 to 4 p.m., 4 to 6 p.m. Location, Lee 309. Nice place. Department conference room, where the big wheels get together. Tomorrow, discussion class, you will rediscuss, given that you did this in 2045, phase diagram for water. Take a look at it. Again, I do not know how textbooks presume to discuss with you phase diagrams for water without having introduced you to all the fundamental aspects of thermodynamics. Because a phase diagram for any substance is a free energy diagram. So how are you to understand what this diagram means if you haven't been introduced to free energy? Well, we won't make that oversight. So I suggest strongly that you take a look at that before tomorrow's gathering. Now, more on fundamentals of thermodynamics. I had intended not to talk about this, but I decided it's very important, so we'll spend some time talking about it. Last time we reminded ourselves that from the first law we get enthalpy, which is really a measure of bond strengths, bond energies, and change in enthalpy from the first law of thermodynamics. Because it's not possible to measure absolute enthalpies, but we can measure changes in enthalpy, which you talked about in great detail in Chemistry 2045. Q, heat flow, a measure of delta H. The problem, however, is even though measuring delta H tells us a lot, it tells us about bond strengths and material stability based on bond strength of reactants versus products. XO, bond strengths are increasing. That's why the reaction is energy liberating. Endo, you got to put in energy to make the reaction occur, because bond strengths are weakening. And you've already recognized, if you want to weaken or break bonds in material, you've got to supply thermal energy to do this. Like breaking hydrogen bonds in water. Cook it on the stove. Evaporate to pull the water molecules apart from each other. That you can make spontaneous at an external pressure of 1 atmosphere if you raise the temperature to 101 centigrade or above. You got any idea what kind of temperature you have to achieve? If, from a delta H0 standpoint, and we'll elaborate on the superscript 0 shortly. Got any idea what kind of temperature you got to achieve if you want to make these bonds break spontaneously? To break water molecules apart? Do you think above 100 degrees centigrade you're creating hydrogen and oxygen? I venture to say it would be quite hazardous to boil water if this was happening. You remember what I did with the boom bottles? Mixture of hydrogen and oxygen? You want to operate in a kitchen with an open flame with hydrogen and oxygen in the atmosphere?
That's extremely high. You said it's like 4,600 Kelvin.
Yeah. Point is, intermolecular attraction forces, hydrogen bonds. I guess we really shouldn't even use the word bonds. Because when we say the word bond in chemistry, we're really talking about an ionic bond, which arises from plus-minus attraction, or these shared electron pair bonds. These are a heck of a lot stronger, by far, than intermolecular attraction forces, of which hydrogen bonds are the strongest, yet broken for water at temperatures above 100 centigrade. You want these water molecules to fall apart spontaneously. You got to get that temperature up to around 4,600 centigrade. That's a heck of a lot higher temperature. In any case, the principal difficulty with talking only about enthalpy and change in enthalpy is that change in enthalpy is in and of itself not a criterion for thermodynamic spontaneity, and that's what we need to know about a reaction. Example, if I remove ice cubes from a refrigerator freezer and put them out here on the lecture bench, what will happen to these ice cubes as we talk? They'll melt. You can do this at home, you know that. You don't even have to do it. You know that happens. Well then, since it's happening, it's spontaneous. Is this a bond improvement or a bond weakening process? Huh? Weakening. Change in enthalpy is against this. Yet it's spontaneous. So how do I use delta H as a criterion for thermodynamic spontaneity when change in enthalpy is against this process, yet it's spontaneous? The answer comes from the second law of thermodynamics, which states that for any spontaneous process, the change in entropy experienced by the universe is favorable. Ultimately, this leads to what scientists talk about as the eventual heat death of the universe. I don't think we've got anything to worry about. Speculations indicate that that is far removed from us by billions of years. In any case, if you take a look at page 20-5, you'll see an example of change in entropy being favorable for the universe. What is discussed on page 20-5 is this process in reverse. Freezing of water liquid in the refrigerator freezer. Some temperature below 0 centigrade. I think refrigerator freezers usually operate at temperatures of about minus 10 centigrade. I'm not exactly sure on that one. The point is, this process we know to be driven by delta H. This is a bond improvement process. If you don't think bonds, hydrogen bonds specifically, among and between water molecules in the solid are not stronger than hydrogen bonds among and between water molecules in the liquid, then do an experiment. Florida students commonly are in the habit of diving into swimming pools. It's fun, pleasurable, particularly in the warm months. And we have a lot of warm months in Florida, which is one of the main reasons why I decided to migrate to Florida. I don't like cold. But where I come from, born and raised in Toledo, Ohio, it was not uncommon, it's not uncommon for Lake Erie to freeze all the way across in good cold winters. You could actually get in a car and drive from Ohio to Canada across Lake Erie in the wintertime. The ice will get about like this. I know, I used to go ice fishing. You get yourself nice and warm by using a big metal bar to break a hole in the ice so you can go fishing. But regarding the swimming pool experience, if you think that hydrogen bonds are not stronger in this stuff than in this stuff, after you've dived into a swimming pool full of water liquid, go up to the north in the wintertime and dive into frozen Lake Erie. When your head meets the ice, you'll say, them damn hydrogen bonds are a hell of a lot stronger in the ice. Because in this case, it'll be your skull that gives way, not the water. Don't do the experiment. Or at least, if you wish to do the experiment, please tell me first so I can contact my attorneys. Because I don't want students coming after me with a suit saying, I fractured my skull doing this experiment that my crazy chemistry teacher told me to do. So, regarding this, clearly this is a process which proceeds with an unfavorable change in entropy. Solid state of a substance is much more ordered, much less random, has a much lower entropy than the corresponding liquid or vapor state of the substance. Well then, if it's true that the change in entropy for the universe is always plus for a spontaneous process, and this process is spontaneous in the refrigerator freezer at, say, minus 10 degrees centigrade, and this process proceeds with an unfavorable change in entropy, how is it that the change in entropy for the universe is plus for this thing? That's what's discussed on page 20.5. Point: when we talk about a phase change, because this is a phase change, the change in entropy is the change in enthalpy for that phase change divided by the temperature at which the phase change occurs. Now the change in enthalpy for this is a number. A number with a minus sign in front of it. Okay? At what temperature is this occurring for water liquid to become water solid? 0 centigrade. Now then, notice that the change in enthalpy for water liquid becoming water solid is minus. Where's the heat going? Because this is a heat liberating process. Where's the heat going when this occurs? To the surroundings. And the surroundings are the freezer compartment, right? So the freezer compartment is absorbing energy, which means the change in entropy for the freezer compartment is plus, favorable. Because that's a plus sign for the freezer, minus sign for the water, plus sign for the freezer. At what temperature is the freezer experiencing its change in entropy? Minus 10 degrees centigrade. So notice that. For the water, it's delta H, a fixed energy quantity associated with this process, divided by 273 K. For the freezer, it's the same energy quantity, but with a plus sign in front of it, divided by 263 K, which is the bigger entropy change, magnitude-wise. That experienced by the freezer or that experienced by the water? The freezer. And that's a favorable change. So when you put these two together, the change in entropy for the system, which is this, plus the change in entropy for the surroundings, which is the freezer, you find that the change in entropy for this spontaneous process is plus. And the combination of the change in entropy for the system plus the change in entropy for the surroundings, that's this. Enough said. Now then, more on entropy. Give you a better conceptual idea what this property of material is all about. Standard molar entropy for a substance. Water, carbon graphite, iron, sodium chloride. Depends on formula mass. With no other factors being considered, the higher the formula mass of a substance, the higher its entropy. Phase. Which phase of matter has the highest entropy? Gas, vapor. Intermediate, liquid, lowest, solid. Temperature. Two identical substances, both in the same phase, but one at a higher temperature than the other, the warmer stuff has the higher entropy. And then structure. I wonder how many of you remember that we asked you about this same consideration. In fact, we told you about this same consideration in Assignment 7, 2045 laboratory, in the discussion. Assignment 7 was the exercise on solutions. Experiment on solutions. C5H12. A Lewis structure for one structural isomer of C5H12. Now then, even though textbooks and organic chemists and the like talk about this as a straight chain molecule, it's hardly straight. There's a model. Now, never mind that some of the hydrogen atoms are simulated by silver knobs with things sticking out. And the rest of them are these white plastic spheres. Because we don't have any more enough white plastic spheres for me to make all the hydrogen atoms out of the same model. Carbons simulated by these black, rather prismatically shaped, tetrahedrally shaped parts. Because the carbon atoms in C5H12 are each hybridized how? sp3, tetrahedral geometry. Okay? So if I show you the model and then show you how the organic chemist will draw this structure on the board, zip, 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 see? Because all they refer to, the organic chemists, when they draw these pictures, and you're going to do this extensively in organic class. If they're only interested in the relative geometries of the carbon atoms with respect to each other for a molecular structure, they draw it like this. Carbon, 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 carbon. Then you can put in the hydrogens as necessary. All these sticks simulate bonds to hydrogen atoms. Because the most common atom bound to carbon for any organic molecule is hydrogen. So the organic chemists save time by not drawing the hydrogens. If it's a different atom, they'll draw it. But when it's hydrogen, they just use these sticks. Like this. Okay? Now then. Here is another structural version of C5H12. Same formula, same composition, but not the same structure. Let's see if I can take this thing apart without too much difficulty. And turn it into this molecule. The question is, which I want you to think about while I remake the model, this structure or this structure? Because if these materials are at the same temperature, clearly they have the same formula mass, they will each be gases, same temperature, so if there's a difference in their entropy, it has to be due to structure. So I'm making the other structure now. Which one has the higher entropy? Or do you think their entropies are identical? If you remember reading the discussion for assignment 745L, you know the answer.
The linear has a higher entropy.
The zigzag straight chain has the higher entropy. That's correct. Why?
Because it's least compact and there's more.
Least compact, okay. In what way does that relate to higher entropy? Now then, a way that I like to talk about entropy is to refer to it as the ability of the molecule in question to distribute its internal energy. How does a molecule distribute its internal energy? It distributes its internal energy by modes of motion, or in a simpler term, wiggling. Here is the second structure. Do you see that this molecule can wiggle along a carbon chain which is 3 atoms long, not longer? I don't care which terminal carbon atom you count from. The longest carbon chain, 3 atoms. But for the other one, the longest carbon chain is 5 atoms, isn't it? So this thing, right here, the one we had the model of initially, this can wiggle along a longer carbon chain, and in so doing distribute its internal energy more effectively. That means its heat capacity is somewhat higher, and its entropy is somewhat higher. This will also have a somewhat higher boiling point, pure this than pure this. Now then, these are not polar molecules, so what do their boiling points depend on? Van der Waals forces, or call them London forces, same thing. Where are Van der Waals forces stronger for pure this than they are for pure this?
Because Van der Waals forces are based on the random alignment of external electrons. So there's more electrons on the outside of the molecule in the linear one.
All right, that's fair enough. What this amounts to is, with the so-called linear molecules, in a bulk sample of that, you've got more atom-atom contacts. Fewer atom-atom contacts. So fewer electron-electron interactions among and between molecules. Because for this isomer, there's no way you can have atom-atom contact of the central carbon atom with like molecules in its central carbon atom. This is blocked by these peripheral CH3 groups. Result? Lower heat capacity, lower boiling point, lower entropy. Not a significantly lower quantity, but still lower. And if you think about it as the notes ask you, there's one other structural isomer for this. Its entropy will be intermediate between these two. That ought to tell you that the reason why the entropy for the other isomer, other structural isomer of C5H12 is between these two is that it has a longest carbon chain 4 atoms. Draw it. We proceed. What is that? What for? If you want, you can look them up. This is N-pentane. This is dimethylpropane. You will not find that on the exam. All right? We proceed. Going through chapter 20, pages 6 and 7. We examine the third law, which provides a criterion for determining absolute entropies for substances, provided that the substance in question will form a perfect crystal at 0 Kelvin. This is why in our table of thermodynamic properties, which you were asked last time to take a look at, you will see entropy values, not delta S's, but entropy values, absolute entropy values reported for the pure substances in that table. But for the same pure substances, you will not see free energy values, nor will you see enthalpy values. You'll see delta H's and delta G's for the substances, because you can't measure delta H. And if you can't measure delta H, because you can't measure absolute enthalpies. Well, if I can't measure absolute enthalpies, then I can't measure absolute free energies, since free energy is dependent on enthalpy. You take away the deltas as G equals H minus Ts. I can get the S, but I can't get the H, so I can't get the G. I can get the changes in G. Now then, from this you'll also see some arithmetic which shows you the origin of free energy and change in free energy, which is the common criterion for thermodynamic spontaneity, based on this arithmetic relationship which ties together change in enthalpy for the process and change in entropy for the process. Now then, let's take a look and see what this means from an arithmetic standpoint. If the change in enthalpy for a process is favorable, exothermic bond improvement, and the change in entropy is also favorable, plus this guarantees delta G to be minus and spontaneous for the process. Example, the combustion of this stuff with oxygen to make CO2 and water at 25 centigrade. We talked about this previously. Why is this stable? Not thermodynamically. This stuff is totally unstable thermodynamically. Stable kinetically. But if delta H is endo, bond disimprovement process, and the change in entropy is also not favorable, minus, this guarantees delta G to be plus. So if you have each of the system components present, reactants and products for a reaction, I use the term anti-spontaneous because a change will occur in that system, but it will not occur left to right, as the equation for the reaction is written in red. It will occur in the reverse direction. Products will convert to reactants. Now then, what if we have a battle between delta H and delta S? For example, the change in enthalpy is endo, again, bond weakening, but the change in entropy is favorable. Or, what if the change in enthalpy is favorable, exo, bond improvement, but the change in entropy is not favorable? Under what conditions will delta G be minus and the reaction system will be spontaneous? If change in enthalpy is against it, but change in entropy is for it. Which of these has to be larger to have delta G be minus spontaneous for this condition? Which one's got to be larger? This has got to be larger. What do we do to make this larger? Heat the damn system up. So we got a handle on making the system spontaneous. Heat the system up, raise the temperature. Conversely, if the change in enthalpy is for it, and the change in entropy is again it, then you want to minimize the change in entropy, which is again the spontaneous nature of the process. So in this case, we need the absolute magnitude of change in enthalpy to exceed the absolute magnitude of temperature multiplied by the change in entropy. So what do we do now to try to cause this process to be spontaneous? Cool it off. Now, one other possibility exists. The change in enthalpy is for it. The change in entropy is against it. But the magnitudes are equal. Or the change in enthalpy is against it, but the change in entropy is for it. But the magnitudes of these terms are equal. Then, delta G0 is 0. The arithmetic tells us so. To what condition do we here refer? Equilibrium. So this gives us our first look at how these fundamental thermodynamic considerations relate to equilibrium, the most stable thermodynamic state in which a reaction system can exist. Okay? Now then, language. Since we are really concerned far more with reaction spontaneity, and for reasons which we discussed in brief last time, the simplest way to get reaction spontaneity is from a delta G0 standpoint rather than from a delta G standpoint, because delta G corresponds to any imaginable set of conditions, any possible set of conditions. But if I use this term with the superscript 0, now I'm referring to a change in free energy for the process under a specific set of conditions known as standard conditions. What are standard conditions? Now, I think the easiest way to conceptualize standard conditions is to recognize what are the possible components of a reaction system. Components. I'm talking about material. What are the possible material components of a reaction system? Pure solids, like calcium carbonate. Pure liquid. Gases. And solutions, which means solute species. Okay? Like calcium ion AQ and carbonate ion AQ, or bicarb ion AQ, things which come from carbonate ion when I make saturated calcium carbonate solution. Under what conditions are pure liquids or pure solids in the standard state? Under what conditions are pure liquids or pure solids in the standard state?
298 Kelvin.
There's no such a thing as a thermodynamic standard temperature. None. Don't get this mixed up with defined standard temperature for gases, which is 0 centigrade. There is no such a thing as a thermodynamic standard temperature. I can do standard state studies for a reaction system under any temperature condition, provided the material components of the system are stable and available at that temperature. That's the only requirement.
They're always in the standard state.
Pure liquids and pure solids, by definition, are in the standard state. That's all. If you are going to study a reaction, like the dissolving of calcium carbonate in water, and you want to do it under standard state conditions, take some calcium carbonate. Because by definition, it's in the standard state. Doesn't make any difference how much you got, it's in the standard state. But keep in mind, you have to also pay attention to phase and the most stable version of this stuff. Calcium carbonate. Do we have any familiarity with calcium carbonate liquid? No. Calcium carbonate gas? No. No. So standard state calcium carbonate is solid. All right? Now then, how about gases? We want gases to be part of a system because the system we wish to study involves these gases. How do I put these gases in the system and have them under standard state conditions?
If at a certain temperature, the partial pressure of the gas is 1.
Never mind temperature.
If the partial pressure is just 1.
If the partial pressure for the gas is
1 atm.
1 atmosphere or 1 bar. Today we use 1 bar. But I think a lot of the data I have in the thermodynamic properties table is still in atmospheres, and there's not a whole lot of error in going from atmosphere to bar, because 1 bar is 1.01 atmospheres. 1%. All right? So we'll stick with atmospheres. And I'll change it to bar later when I got time to operate on the data and change the data that's necessary. Now, the other possible system component is a solute. Under what conditions is a solute species present in the standard state? 1 molar. That's right. Now, some thermodynamic studies involve 1 molal. Did you do molal concentrations in 2045? Yeah. We'll stick with 1 molar. All right? That takes care of the superscript 0. What's this mean? If I ask you to tell me the meaning of sub F on this term, and the question's worth 10 points, and your response is formation, you get a half a point if I'm in a good mood. I want to know formation of what, and I want to know formation from what. What does that sub F mean? What does it mean?
Formation of 1 mole of products.
1 mole, it means forming 1 mole. So I'm going to write down, consider delta G0 sub F for 1 mole of this stuff with which we are hardly familiar at all. Ha ha ha. Water liquid. What's sub F mean? We talked about the fact that sub F means you're going to consider making 1 mole, because the change in free energy is greater if you make more than 1 mole, and the change in free energy is smaller if you make less than 1 mole. You know doggone well, if I burn 1 log in the fireplace this size, I am not going to get as much heat as if I burn 10 logs the same size in the fireplace. So when you talk about these free energy, these thermodynamic terms, delta S, delta H, delta G, you've got to talk about material quantity. 1 mole means you're going to make 1 mole of the stuff. From what? Why?
Because that's their standard state.
Their standard states. You're there, but you're there not saying it as sharply and clearly as I like. The sub F means that you're considering formation of the substance from the required quantities of the most stable allotropic versions of the substance's component elements. There's lots of ways to make water. But when I see the sub F for any substance, I'm talking about making that stuff from its component elements. So now I have to decide. What are the most stable allotropic versions of the component elements of water? Well, specifically, we're talking then about hydrogen and oxygen. What's the most stable allotropic version of hydrogen? H2. How many allotropic versions are there of elemental oxygen? How many allotropic versions are there of elemental oxygen? 3. O atoms, O2 molecules, and ozone. Which is the most stable allotropic version? Bingo. So if by direct measurement I want to get delta G sub F super 0 for a mole for water liquid, then I got to consider making a mole of water liquid from a mole of this stuff and a half a mole of this stuff. And nothing else will do. Now, just to try to be sure you are on top of this, there's a gas stuff. OCS. I call it my officer's candidate school molecule. OCS. Is that officer's candidate school? OCS. Officers Candidate School. This is structurally analogous to what molecule with which you are familiar? Carbon dioxide. A linear molecule, two sets of double bonds. On your paper right now, write the reaction equation for which, if you were able to run the reaction and measure the change in standard free energy, you'd get delta G sub F super zero for OCS. What is the reaction equation? Now, we've already recognized the most stable allotropic version of oxygen is this. So I'll write this down for starters.
Would it be the same thing if you wrote 1 mole of O2 and 2 moles of H2?
Nope, because then you're doubling quantity. 1 mole. You got to consider making 1 mole. What is the most stable allotropic form of sulfur? S8. So I'm going to add 1/8 of a mole of S8, which is an amorphous yellow solid. And now that leaves me with one question to answer. I want you right now, our last consideration for today, you look at the thermodynamic properties data table. Right now, open it up. I want you to look for carbon. We're trying to determine between the two allotropes of carbon, graphite and diamond. Graphite and diamond. Which is the more stable allotropic version? Graphite or diamond? You see the table tells you it is graphite or diamond? Graphite. Now then, question. Why is graphite more thermodynamically stable than diamond, given, for example, that you know diamond is a hell of a lot more durable material? Why is it the case, nevertheless, that carbon graphite is more stable thermodynamically than carbon diamond? I want you to research that before our next talk, and we'll start with that on Wednesday. Remember, tomorrow, phase diagram water.